Welcome to the closing lecture of the MOOC Energy Supply Systems for Buildings. Great that you made it to the end. You first have learned how to estimate the primary energy needed to meet a certain demand for heat, cold and electricity in a building by using the efficiency of the conversion system and the energy content of the resource used. You have practiced a lot that there is sometimes only one step between primary energy and energy demand, like when a combustion boiler is used home. Other times there are two steps, like when using an electrical boiler or a hydrogen fuel cell. Both electricity and hydrogen must be converted from primary resources. You also learned and practiced skills about converting primary energy into kilogram and cubic meters of resources and into CO2 emissions. You know the concepts of country electricity mix and emission factors depending on the type of resources used to produce electricity and the conversion efficiency. This is widely used in many national and international policies and building regulations and is essential to counteract climate change. You then learned about all important technologies used to produce heat, cold and electricity. Although the table looks quite simple and embraces indeed all main technologies, the discovery journey has been quite intensive, as were the calculations for size, costs, resources and CO2 emission estimations. But you know now the principle. During the first week, you studied the performances of electrical heating and combustion boilers. During the second week, you got acquainted with heat pumps that concurrently produce heat and cold and are therefore also chillers. You additionally learned about geothermal heat, ATES systems, evaporative cooling and environmental cold. During week 3, conventional energy generation was handled, as well as the use of the resulting waste heat in so-called cogeneration plants. Renewable-based turbine technology was handled as well, with geothermal steam, hydropower and wind turbines. Finally, you learned about hydrogen technology in fuel cells for cogeneration. During the last week, you have learned about solar technologies for heat and electricity and exercised your knowledge on buildings in order to design a suitable conversion system while keeping costs acceptable, using a minimum of natural resources and producing a minimum of carbon emissions. I hope you have enjoyed this journey. Each lecture in this course and almost each slide in each lecture would have been worth a complete course. You have learned about the working principles, but for each principle there are tens of possible variations and hundreds of issues we did not handle. For instance, how burners of boilers need to be changed when converted from gas to biomass or hydrogen, or how to combine heat pumps in parallel or series to obtain higher temperatures or capacities, or what are the developments in the field of refrigerants or of electrolytes for fuel cells. Shortly, we did not go into any design and development issues. We did not really handle energy from burning domestic waste. We just classify it into waste heat, which is a bit short. We talked a bit about smart electrical and heating and cooling grids, but did not handle them. Of course, they are not a conversion system, but a distribution system, but still of main importance for the development of renewable energy. We did not look at the social and organizational processes that could help to realize the transition to renewables, neither what it would mean for the geopolitical balance to concentrate world's energy generation in desert areas. We also did not discuss carbon capture technology. Although this technology may be useful during a transition period, and it is an interesting approach to capture the carbon in air to mineralize it and put it back into the ground, it seems better to use technologies that do not produce CO2 and do not deplete natural resources. And most important, we did not consider all important environmental impacts of energy supply. We limited ourselves to resource depletion, the category abiotic depletion on the slide, and to CO2 equivalent emissions, which is the global warming category on the slide. As you see, there are many more impacts. Ozone layer depletion, we touched on it when looking at refrigerants, photochemical oxidation, which is nothing else than smog, toxicity for humans and ecosystems, acidification, eutrophication because of fertilizers, and of course radiation. What we also did not consider are the environmental impacts of making PV cells and wind turbines or an hydropower plant. Well, these impacts coming from material extraction, transportation, and manufacturing have been taken into account in this picture, while the impacts of building a traditional or nuclear plant were not taken into account. What you see on this picture is the relative impact of the generation of 1 kilowatt-hour electricity depending on the resource used to make this electricity. In red, we have the Dutch electricity mix, which consists of 57% of gas and a bit of coal. In blue, the one of Norway, which is 100% hydropower. In grey, the French one, for more than 95% nuclear energy. And then in yellow, PV cells, and in dark blue, wind turbines. All these environmental impacts have another unit, so you cannot compare between them. But to show all of them in one figure, I have normalized all environmental impacts to 100 for the Netherlands. So what you see are the relative differences. The data may not be completely up to date, but it shows clearly the trend. It is clear that all options perform much better than the Dutch electricity mix, except for the environmental impacts relating to ecosystem toxicity. This has to do with mining and production processes of the materials used and the on-site issues for hydropower. This means that a lot of work has to be done to reduce these impacts. Finally, the huge impact of nuclear energy in the category radiation should be noticed. Solving all these environmental problems is a huge challenge, and this figure shows the immensity of the task. The world's primary energy consumption is still growing quickly, and despite all developments, most of it is still fossil fuel. So, you have a tremendous task to achieve. There is a lot of research going on to improve existing technologies or make them market-ready. There are also interesting developments in the field of blue energy, making use of the temperature differences between deep and surface ocean water, or making use of osmosis by using the differences in concentration between salt ocean water and fresh water. There are developments in providing each appliance with its own embedded energy system by making electricity from air or from soil vibrations. Even using potential difference in plants is researched. And in the field of building technology, we have a lot to expect from the integration of energy supply into the building itself and in the facade in particular. Think of smart glass with adaptable properties, or with integrated PV, heat pumps integrated in the facade, phase change materials, etc. I hope this gives you inspiration to continue learning about buildings as sustainable energy systems. I also would like to thank you for participating in the course. It has been for us a great experience. I wish you good luck and maybe see you in another MOOC. The next one is about thermal comfort and health in buildings, and the last one of the PCP will be about the design of HVAC systems, in which all three precedent courses come together. Goodbye and thank you.